Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we employed the concept of the singular value decomposition of a MIMO channel and reduced it to a decoupled MIMO wireless channel as y tilde equals the diagonal matrix sigma times x tilde plus n tilde bar, where this is arrived at, as we said, by multiplying y with u Hermitian and pre-coding the transmit vector x as x equal to v times x, and we said as a result I have y1 tilde equals sigma 1 x1 tilde plus n1 tilde, y2 tilde equals sigma 2 x2 tilde plus n2 tilde, so on and so forth. So, this MIMO channel has become decoupled into T parallel channels. This is also, as we said, spatial multiplexing. And we also described this schematically. We drew a picture. We said it can be considered as T different channels with x1 tilde transmitted as P1, gain sigma 1, noise n1 tilde, x2 tilde transmitted across channel with gain sigma 2, n2 tilde noise, so on and so forth. We also said the capacity of this channel is the sum of the capacities of these T individual channels, that is log 2 1 plus pi, which is pi is power allocated to ith channel, sigma I square divided by sigma n square summation over the T channels, and we want to maximize this capacity such that this transmit power P1, P2, Pt allocated to each of the T channels is limited by P, which is the total transmit power. We said we solved this optimization problem and we said the optimal allocation is P I equals 1 over lambda minus sigma n squared divided by sigma I square. Keep in mind, sigma n squared is the noise power, sigma I squared is the singular value, that is the gain associated with the ith channel. So, there is a difference between these two sigmas. The plus indicates that it is equal to this quantity if it is greater than 0, simply 0 if it is less than 0, because power cannot be less than 0. And we also started with an example of this channel matrix H 2 minus 6 0 3 4 0 0 0 2. We computed its singular values as follows, that is square root 52, square root 13 and 2, and corresponding to these singular values we were about in the process of computing the optimal power allocation towards capacity maximization. So, with that let us proceed into today's lecture. So, the capacity can be, as we said, it can be represented as log 2, there are 3 channels, 1 plus P1 sigma 1 square divided by sigma n square plus log, I will drop the base 2 here because it is obvious from the context, plus log P2 sigma 2 square divided by sigma n square plus log 1 plus P3 sigma 3 square divided by sigma n squared, right. P1, P2, P3 are the powers allocated to channel 1, 2, 3 respectively. Sigma 1, sigma 2, sigma 3 are the singular values of these 3 channels, nothing but the gains of these 3 channels, and sigma n squared is the noise power. This can be represented as log 1 plus sigma 1 square is 52. So, this is P1 into 52 divided by 2 plus log 1 plus P2 into 13 divided by 2 plus log of 1 plus P3 into 4 divided by 2 as sigma 3 square is 4. So, this is the capacity optimization that we want to look at. Of course, this is subject to the constraint that P1 plus P2 plus P3 is less than or equal to 0.75, that is the total transmit power, that is the total power available with the transmitter. And we said we have to follow an iterative procedure where first we set n equals t equals 3. Now, what I am going to do is I am going to iteratively solve this thing 1 by lambda minus sigma square, sigma n squared by sigma 1 squared, that is 2 divided by 52, which is 1 by 26, plus 1 by lambda minus 2 by 13 plus 1 by lambda minus half equals 0.75. I can solve this as follows: 1 by lambda equals 0.75 plus 1 by 26 plus 2 by 13 plus half divided by 3 equals 0.48. So, computed corresponding to this assumption, the lambda value is 0.48. Now, I am going to back substitute lambda and check is 1 by lambda in fact is 0.48. I am going to back substitute this and check if the powers are consistent, that is every power should be greater than 0. So, now I go back and I verify this for P3, P3 equals 0.48 1 by lambda minus sigma n squared by sigma 3 squared, which is sigma n squared by sigma 3 squared, which is 2 divided by 4 equals half. So, 0.48 minus half equals minus 0.02, which is less than 0. Hence, this is not consistent with our assumptions. The only thing this means is that P3 is 0, that is the third mode is allocated 0 power. Hence, P3 equals 0. Now, what I will do is I will set n equals t minus 1, that is n equals 2, and now I will resolve this thing. Now, I will resolve this thing as 1 by lambda minus 1 by 26 plus 1 by lambda minus 2 by 13 equals 0.75, 1 over lambda equals 0.75 plus 1 over 26 plus 2 over 13 divided by 2 equals 0.4712. Okay. So, now I will again go back and see if the computed powers are greater than 0. P1 equals 0.4712 minus 1 by 26 equals 0.4327. This is greater than 0. In fact, I will express this in dB. So, I will do that later, and P2 equals 0.4712 minus 2 by 13 equals 0.3174. Now, you can see both the computed powers are greater than 0. You can see this, they are greater than 0. Hence, this is consistent with our assumptions. So, these are the optimal powers. The procedure now terminates. Hence, these are the optimal powers, and in fact, P3 equals 0. So, optimal powers are P1 equals 0.4327. However, powers have to be expressed in dB. So, I take 10 log 10 P1, which is minus 3.63 dB. P2 equals 0.3174, taking 10 log 10 of that, that is minus 4.98 dB, and P3 equals 0. These are the optimal allocated powers. And what is the maximum capacity corresponding to this thing? The maximum capacity corresponding to this thing, as we said, is C max equals log 2 to the base 1 plus 52 into 0.4327 divided by 2 plus log 2, this is the capacity of channel 1, plus log 2 into 1 plus 13 into 0.3174 divided by 2, and channel power 3 allocated to channel 3 is 0. So, that capacity is 0. So, this is simply nothing but 5.23 bits per second per hertz. So, you can verify this is 5.23 bits per second per hertz, that is the maximum capacity corresponding to a total transmit power of 0.75, that is minus 1.25 dB, and corresponding to noise power of 3 dB, that is 2. All right. However, this does not essentially complete the procedure. There is one small part left, which is how to do the transmission. Remember, we still have to indicate what are the vectors that are to be transmitted from the transmitter. Let me for an instant go back to the SVD of this matrix. From the SVD, we notice that the matrix SVD equals U sigma V Hermitian. From the SVD, we notice that the matrix V is nothing but, or V Hermitian is nothing but 0 1 0 1 0 0 0 0 1. Hence, this is the row V 1 Hermitian, V 2 Hermitian, V 3 Hermitian. Notice that we have to pre-code the transmit symbols with this. Hence, the actual transmit vector x bar, is given as V 1, V 2, V 3. These are the columns V 1, V 2, V 3 times x 1 tilde, x 2 tilde, x 3 tilde. However, x 3 tilde is allocated 0 power. So, I will remove this. Hence, this is simply V 1 times x 1 tilde plus V 2 times x 2 tilde, which can be written as vector 0 1 0 times x 1 tilde plus vector 1 0 0 times x 2 tilde. Remember, these are the vectors V 1 and V 2. These are also the beam forming vectors. Remember, you cannot simply transmit any transmit vector, but you have to pre-code whatever transmit symbols are there with this transmit with this matrix V, right. That is what we said, that is what results in the decoupling. And now, this is easy. X 1 tilde is nothing but you have to allocate power P 1 to it. So, this is square root of P 1 into B 1, where B 1 is a unit power symbol. This is square root of P 2 into B 2, where B 2 is a unit power symbol. Computing P 1 and P 2 as before, this is nothing but 0 1 0 times 0.66 B 1 plus 1 0 0 times 0.56 into B 2. All right. So, this is x bar, which is vector V 1 times 0.66 B 1 plus vector V 2 times 0.56 B 2. This 0.66, 0.56 are essentially the square roots of the optimal power to maximize capacity. This is square root of P 1, 0.56 is square root of P 2, and B 1 and B 2 are unit power constellation symbols. These are unit power symbols. All right. So, this is the allocation that maximizes the capacity. This can be anything, this can in fact even be coded symbols. All right. So, if you need some code to achieve the capacity, B 1 and B 2 can in fact be coded symbols. All right. So, this is the complete transmit scheme, that is you beamform in these directions, that is you employ vectors V 1, V 2 to pre-code and transmit them with the appropriate powers to maximize the capacity. And this is the transmit vector, this is the actual transmit vector. This is the transmit vector to maximize capacity. All right. So, this is the transmit vector that maximizes the capacity. all right. Before we move on, let me do another again a very small idea here. How do essentially how do you characterize, because we still haven't characterized what are the capacity advantages of a MIMO system. So, I am briefly going to look at a notion of asymptotic capacity. We have seen that the capacity of a MIMO system, is log 2, or it can be shown that the capacity of a MIMO system is log 2 sigma n squared h r x h Hermitian. Let me explain the different terms. This is the log. The modulus here in fact indicates the determinant. This is the determinant of the matrix inside, all right. This is the noise variance, H is the channel matrix, and R x is known as the transmit covariance. That is, it shows the power profile of the transmitter symbols. In fact, R x equals expected x bar Hermitian. This is the transmit profile. What this shows is what are the powers allocated to the different transmit symbols from the different antennas. Already you might remember it, we have considered the transmit covariance even in the case where we derived the MMSE estimator. Okay. Now, what I am going to assume here is I am going to assume a simple transmit covariance structure. I am going to assume that the power, whatever power P is available at the transmitter, is distributed uniformly across all the transmit antennas. That is, each transmit antenna is allocated a power P over T. Hence, my transmit covariance R x equals P T over T I. This is the transmit covariance. Hence, we have C, the capacity using this transmit covariance is modified as log 2 P T over T sigma n squared H Hermitian. Now, what I am going to assume is I am going to make a slightly modified assumption to illustrate what I mean by this asymptotic capacity. I am going to assume that T is much greater than R. This is however not unlike what we were assuming earlier. We always assume the case that R is greater than or equal to T. Just for this section, I am going to slightly modify that assumption. I am going to see what happens as the number of transmit antennas increases much larger compared to the number of receive antennas. What we have in that case is, let me look at the structure of this matrix. I want to look at the structure of this matrix H Hermitian. If I look at the structure of that matrix H Hermitian, now remember R is much smaller than T, or T is much greater than R, which means the rows there are many more columns than there are rows, which means the size of each row is fairly large compared to the number of columns. So, we have a number of rows. So, we have H1 Hermitian, let me denote this by H1 Hermitian, H2 Hermitian, so on up to HT Hermitian. These are the different rows into H1, H2, H R, all right, and these are the different columns, all right. Now, this matrix can be simplified as H1 Hermitian, H1, H2 Hermitian, H2, so on, HR Hermitian, HR, and the off diagonal terms are clear: H2 Hermitian, H1, H1 Hermitian, H2, and so on. Now, observe each of these diagonal terms, that is, look at the diagonal terms. They are H I Hermitian H I, which is simply the dot product of each row with itself, and this tends to, this is equal to norm H I square, that is the norm of a vector of length t, all right, and this tends to, remember we assumed that each coefficient is average power 1. So, this tends to t, all right. Also H I Hermitian H j, when I not equals j, remember we said these different elements are uncorrelated, hence this tends to 0, all right. So, H the matrix H Hermitian for large number of transmit antennas compared to receive antennas looks as follows. It looks as T, T, T and zeros on the off diagonal. In fact, this should not be equal to, this should be a tends to, all right, which is nothing but T times identity matrix, T times the identity matrix of size R, because H Hermitian, remember, is of size R. So, I am going to take that and I am going to substitute it in the expression we had earlier, which is log 2 I plus P t over T sigma n squared H Hermitian. Asymptotically, this looks, hence asymptotic capacity, C asymptotic equals log 2 I plus 1 by sigma n square P t over T into H Hermitian, we said is T times identity, hence this is nothing but log 2, look at this, the T's cancel, hence this is nothing but log 2 I plus P t over sigma n square, where P t is the total transmit power, this is the total transmit power. Okay, times identity, and this you can see is nothing but, you can see this is nothing but R times log of to the base 2 1 plus P t over sigma n square. Why does this follow? Because if you look at the structure of this matrix I plus P t over sigma n squared I, this matrix is nothing but this matrix is nothing but 1 plus P t over sigma n squared, 1 plus P t over sigma n squared, 1 plus P t over sigma n squared, and the off diagonal terms are all 0. Hence, the determinant of this matrix is nothing but 1 plus P t over sigma n squared to the power of R, and when you take log of the determinant, that is nothing but log R times log 1 plus P t over sigma n squared. Hence, we have C asymptotic R times log 2 1 plus P t over sigma n square, where P t is the total transmit power. This is the total transmit power. Now, you can see from here clearly that asymptotically the capacity increases as R, which means the more number of receive antennas you have, it increases linearly with respect to R, and also you can observe more importantly that this is for the same transmit power. I am not increasing the transmit power, this is for constant. So, I have a MIMO system. In a MIMO system, the capacity is increasing linearly with respect to R and same transmit power. Just because simply because I have more transmit antennas, I am not increasing the transmit power. For the same transmit power compared to a single input single output system, my capacity is asymptotically increasing linearly with the number of antennas. In fact, I will write this as, remember, T is much greater than R. So, R is nothing but the minimum r comma t. Hence, I will write this as minimum of r comma t log 2 of 1 plus p t over sigma n squared. Log 2 of 1 plus p t over sigma n squared is nothing but the size of channel capacity. If I had a single antenna, my capacity would be log 2 1 plus p t over sigma n squared. This part is nothing but the SISO capacity. This increase here, the minimum of R t is nothing but the spatial multiplexing gain, the capacity gain that is arriving because you are transmitting many information streams in parallel. Precisely how many information streams? This is minimum of R comma t. This is nothing but MIMO increase in capacity. Hence, a MIMO system essentially results in an increase in capacity that is proportional to minimum of R comma t. For instance, if you have let us say 4 receive antennas and 10 transmit antennas, your capacity rises as a minimum of R comma t, which is minimum of 4 comma 10, which is 4. So, it is for the same power you get a 4 times increase in capacity asymptotically. That is what this result says. So, that is the big gain of a MIMO system, which is nothing but it results in an increase in capacity, a significant increase in capacity, which is a key part of every 3G and 4G wireless system, because remember, as we said in the first lectures, for 3G 4G wireless systems are based on broadband wireless access, that is they want to provide high data rates so that you can use them not only for voice, but video and so on applications. So, MIMO is a key technology that makes this possible in 3G and 4G wireless communication systems. All right. So, with that I will move on to the next topic in MIMO communication system. So, that brings an end to the capacity characterization. Now, let us move on to another important topic in MIMO systems, which is space time coding. So, I will start with a description of the Alamuti code. So, before I start with the description of the Alamuti code, I want to mention something. I am going to consider a 1 cross 2 system. So, it is not exactly a MIMO system, it is rather multiple transmit antenna, one receive antenna. We have not dealt with this kind of system explicitly before, all right. We have seen multiple receive antenna, single transmit antenna, but we have not looked at what happens when you have multiple transmit antenna, single receive antenna. So, I am considering a 1 cross 2 system, which is single receive antenna, multiple single receive antenna, multiple transmit antenna system. And so, that system, the channel matrix is H1 comma H2, where H1 and H2 are coefficients. So, look at this, I have one receive antenna, two transmit antennas, and my system model can be expressed as what is the 1 cross 2 system model, that can be expressed as the received symbol y equals H1 H2, which is my 1 cross 1 my system, times x1 x2 plus n. Okay. What is this x1? x1 is nothing but symbol transmitted from transmit antenna 1. X2 is symbol transmitted from transmit antenna 2. Symbol transmitted from antenna 2, alright. So, x 1 is the symbol transmitted from transmit antenna 1, x 2 is the symbol transmitted from antenna 2, alright. So, I have y equals h 1 h 2 x 1 x 2 n. Now, how do we do transmission in this case when we have two transmit antennas and one receive antenna? Let me illustrate to you a simple scheme. Transmit antenna scheme for a transmission scheme for a 1 cross 2 system to obtain diversity. First of all, the question we want to ask is, in this system is it possible to obtain diversity? Because remember, we said when we have multiple receive antennas and single transmit antenna, we could obtain a diversity gain. Now, is the same thing possible when you have the other case, that is multiple transmit antennas and single receive antenna? Can we still obtain diversity gain? Let me illustrate to you a simple scheme. Consider a symbol x. What I am going to transmit from the transmit antennas is x 1 equals h 1 conjugate divided by norm h times x. So, it is sort of pre-coding. When I have x, I want to transmit x, from transmit antenna 1 I am transmitting h 1 conjugate divided by norm h times x. From transmit antenna 2 I am going to transmit h 2 conjugate divided by norm h times x. Hence, this can be represented as a vector h 1 conjugate divided by norm h, h 2 conjugate divided by norm h times x, all right. So, I am going to transmit x 1 x 2 x 1 x 2 as h 1 conjugate over norm h, h 2 conjugate over norm x times x, where x is the actual modulated information symbol. This is also similar to the pre-coding that we saw in the singular value decomposition. Remember, before transmission of the vector, we obtain the vector x as v times x tilde. This is something similar, except now here it is not a matrix, but a single vector. This also has a name in the context of wireless communication. This is known as beam forming, that is, you are directing your beam in this direction, and more precisely this is known as transmit. This is known as transmit. This is known as transmit beam forming. Now, let us see what happens when I transmit this symbol here or this vector here across the 1 cross 2 1 cross 2 channel, that is y equals h 1 h 2 into h 1 conjugate divided by norm h, h 2 conjugate divided by norm h into x plus n. This you can see is nothing but h 1 conjugate, that is magnitude h 1 square, plus h 2 conjugate magnitude h 2 square, that is norm h square, divided by norm h, which is nothing but norm h times x plus n. And now we are in business, because we see SNR is nothing but norm h square times p, where p is the transmit power, divided by sigma n square. So, we look at the SNR of this system, that is nothing but norm h square times expected x square, which is transmit power in p, divided by sigma n square. Hence, the SNR is exactly same as that of maximum ratio combiner, exactly as MRC. Hence, what this says is that if you can do this at the transmitter, then it does not matter if you have more transmit antenna, single receive antenna, or more receive antenna, single transmit antenna. You can transmit in such a way that you can get the same performance that you get as the maximum ratio combiner, that is diversity order 2 in this case. Now, is that so? This is similar to, this says Tx diversity is similar to Rx diversity, that is having multiple transmit antennas is similar to having multiple receive antennas, but this is this exactly the same thing. is having multiple antennas at the transmitter exactly same as having multiple antennas at the receiver. Let us go back to what we have done. We have done a transmit precoding where we said the transmit vector is H1 conjugate divided by norm x, H2 conjugate divided by norm h times x. Now, can this be done at the transmitter? Can this operation be done, or can this operation be done at the transmitter is the question which we want to ask ourselves. To be able to do this at the transmitter, we require knowledge of H1 and H2, which are the channel coefficients. So, these are the channel coefficients. This is termed as, remember the wireless channel is changing, this is termed as channel knowledge or channel state information. So, this is termed as channel state information or CSI. Remember, since you are transmitting from the transmitter to the receiver, it is easy to estimate the channel at the receiver and obtain channel state information at the receiver. However, to employ this at the transmitter needs channel state information, which means that information has to be relayed back to the transmitter. Hence, this is only possible if knowledge of the channel coefficients is available at the transmitter. Hence, transmit beamforming is only possible when channel knowledge or channel state information is available at the transmitter. So, this is not always possible, and obtaining channel state information at the transmitter is much more difficult than channel state information at the receiver. That is why MRC, maximal ratio combining, is possible at the receiver. However, this scheme, which is maximal ratio transmission, performing at the transmitter is much more difficult. Hence, obtaining transmit diversity is challenging compared to obtaining, hence obtaining transmit diversity is challenging compared to obtaining receive diversity. That is one of the key challenges in this context. What you want to discuss next is what is known as the Alamuti code. What is the Alamuti code? Alamuti code is a space time code, which is about Alamuti code. I am going to list the salient points here. It is a space time code proposed for 1x2 or single receive antenna, 2 transmit antenna, wireless systems. It is a space time code. Alright, that is the key. This is a space time code. In fact, it is a space time block code. as we are going to look at later, and it achieves a diversity order of 2. Remember, it has 2 antennas, so full diversity is diversity order 2. So, it achieves a diversity order 2 and without channel knowledge or channel state information CSI at the key here is it achieves a diversity order 2, however, it does it without CSI, that is without the need for channel state information or channel knowledge at the transmitter. That is the unique feature of the LMUT code. That is what we are going to discuss next. So, we are going to consider a 1x2 system. So, I am going to consider a 1x2 system, that is, so let me illustrate the LMUT code. It is a 1x2 system, one receive antenna. So, I am going to consider a 1x2 system, which means one receive antenna and 2 transmit. It has one receive antenna and 2 transmit antennas. At the first instant, so we consider 2 symbols, consider 2 symbols x1 comma x2. We consider 2 symbols x1 comma x2. At the first instant, we transmit the transmit vector x1 comma x2. So, I am considering a 1x2 system to illustrate the LMUT code. I am considering 2 symbols x1 comma x2. At the first instant, I am going to transmit the vector x1 comma x2, which means from transmit antenna 1 I am going to transmit x1, from transmit antenna 2 I am going to transmit x2. So, x1 is transmitted from transmit antenna 1, x2 is going to be transmitted from transmit antenna 2, okay, which means this received symbol in the first time instant y1 can be expressed as h1 x2 x1 comma x2 plus n. So, this can be expressed as y1 equals h1 h2 times x1 x2 plus n. This is for the first instant. This is, let me characterize this, this is for the first transmit, this is for the first transmit instant y1 equals h1 h2 times x1 x2 plus n. Now, for the second transmit instant, I will do something interesting. What LMUT has proposed is something very interesting. For the second transmit instant, consider the same symbols x1 and x2, however, transmit them as follows. Transmit vector equals, the transmit vector for the second transmit instant is minus x2 conjugate x1 conjugate. That is, I consider the same symbols x1 and x2 which were transmitted in the first transmit instant. In the second instant, I transmit minus x2 conjugate from the first transmit antenna and x1 conjugate from the second transmit antenna. So, I will have here minus x2 conjugate from first transmit antenna, and this x1 conjugate from second transmit antenna. I transmit minus x2 conjugate from the first transmit antenna, x1 conjugate from the second transmit antenna. Hence, this is given as what I receive y2 is given as h1 h2 minus x2 conjugate x1 conjugate plus n2. This is given as h1 h2 into minus x2 conjugate x1 conjugate plus n2. I will make slight modifications to this. First, what I will do is, after receiving y2, I will consider y2 conjugate. So, I will consider y2 conjugate at the receiver. I am going to process this as follows. Y2 conjugate is nothing but h1 conjugate h2 conjugate minus x2 x1 plus n conjugate of 2. So, I am receiving y2 corresponding to the second transmit instant, and I am taking its conjugate. Now, I will just rewrite this as follows. Y2 conjugate equals, now instead of having the minus symbol at x2, I can shift that minus symbol to h1 conjugate. So, this becomes minus h1 conjugate h2 conjugate x2 x1 plus n conjugate 2, and now I will make one final modification, that is, I will flip the order x1 x2. This, remember, this is not flipping the order on the transmit antennas, this is just mathematical notation. Instead of writing h1 h2 conjugate, I will flip this as h2 conjugate minus h1 conjugate. Similarly, I will flip the x1 x2 here. Hence, I will be able to write this as y2 conjugate equals h2 conjugate minus h1 conjugate x1 x2 plus n conjugate of 2, and now I am in business. Now, what I will do is I will stack these symbols, stack y1 and y2 conjugate as, now I will stack y1 and y2 conjugate as y1 y2 conjugate equals, and you can verify this, this can now be written as h1 h2 h2 conjugate minus h1 conjugate x1 x2 plus noise n bar. So, by stacking these symbols, what I have done is I have taken this 1 cross 2 system and I have effectively converted it into a 2 cross 2 MIMO system. Look at this, this is the matrix h1 h2 h2 conjugate minus h1 conjugate. So, I have effectively converted this into 2 cross 2 MIMO system. So, now what I have is effectively converted into a 2 cross 2 by this intelligent scheme suggested by Alamuti. I have taken a 1 cross 2 system, I have effectively converted into a 2 cross 2 MIMO system. In fact, this is column 1, this is column 2. Now, in fact, you can see that column 1 is orthogonal to column 2. For instance, if I look at C1 Hermitian C2 dot product of column 1 column 2, that is nothing but H1 conjugate H2 minus H2 H1 conjugate, which is 0. Hence, column 1 column 2, hence C1 and C2, that is column 1 and column 2 are orthogonal. So, I have a very interesting property here. I have taken a 1×2 system and employed the scheme suggested by Alamuti, and what I have done is I have the 1×2 system is converted into a 2×2 MIMO system by this intelligent transmission scheme, such that column 1 and column 2 are orthogonal. Now, what I can do here at the receiver is something interesting. Let me illustrate this to you. I can in fact employ each column as the beamformer after normalizing it. For instance, W1 can be employed as W1 equals H1 divided by norm H, and H2 conjugate divided by norm of H. Okay. I will employ this as the receive beamformer, that is I will multiply. So, I will employ this as the receive beamformer. So, what I am going to do is I am going to perform W1 Hermitian y bar. So, I am going to perform W1 Hermitian y bar, which is nothing but H1 conjugate divided by norm H, H2 divided by norm H into H1 H2 or H2 conjugate plus W1 Hermitian n bar. I will denote this by some n1 tilde. You can observe this is nothing but H1 conjugate H1, which is norm, which is magnitude H1 square, plus H2 conjugate magnitude H2 square divided by norm H, which is magnitude H, and this is orthogonal to this 0 times, I am sorry, I have to have an x1 x2 over here, 0 times x1 x2 plus n1 tilde, this is nothing but norm H times x1 plus n2 tilde, and this I can use to decode x1, and you can clearly see from this magnitude of H here that I can obtain diversity. This is in fact diversity order 2. So, due to lack of time, I will stop this here at this point, and we will continue from this point in the next lecture to illustrate further properties of the Alamuti code. Thank you.